Good morning, ladies and gentlemen. In terms of this presentation, we are going to look at the impact that cyclones have on a milling circuit. It is not very difficult to understand, but sometimes people tend to get confused. So I'll be looking at the cyclone basics, briefly at the basics, just to get you all on the same level. Factors affecting the hydrocyclone performance, moving on to open circuit milling, closed circuit milling, closed circuit optimization, circuit checks, and then some general guidelines. So in terms of cyclone basics, the hydrocyclone, the feed is introduced tangentially. The feed consists of water and solid material. Because it's introduced tangentially, a swirling motion develops inside, or rotational motion develops inside the cyclone. Fine fraction of material migrate to the center, and it will then leave through the vortex finder. The coarser material migrates to the outside, and that leaves then through the spigot. The forces that's applicable here is drag forces, water that migrates to the center, drag the fine material to the center and through the vortex finder, and then the coarser material, centrifugal forces, force the particles to report then to the outside. So in this video, just giving you a brief indication of what is happening inside a hydrocyclone. You see the air core in the center, and then the fine particles that is rotating. Point to take note here. The time that particles spend inside a cyclone is limited. So we need to develop conditions to ensure the unit operates as efficiently as possible. Factors that affect the hydrocyclone performance. The hydrocyclone is not a perfect separator. You've got short circuiting of coarse material to the overflow, and you've got fine particles that's reporting to the underflow that should actually not be there. So the coarse material is getting misplaced via a short circuiting mechanism where material hugs the roof of the cyclone inlet, moves down the vortex finder, and it then slips out. In case you do not believe me, just have a look at this video. Air core, vortex finder, and the air bubbles is then giving you an indication of the flow patterns that is then present next to the vortex finder. Then we've got fine material that's getting short-circuited to the underflow. That's material that enters into the cyclone and is then positioned against the side of the hydrocyclone. It migrates then all the way down and leaves through the underflow. So some of the mechanisms, entrapment, where the material can maybe not pass through the layer of material that's in front of it. And that's also quite applicable when you've got very dense separations or dense liquid densities or slurry densities inside the cyclone. Viscosity starts to become a factor to keep in mind. Then we also have a mechanism where if the particle sits at the side of the hydrocyclone, there's two forces, a drag force and a centrifugal force. But if the particle sits on the side of the cyclone against the wall, there's no water behind it. So there's no mechanism to start, the drag mechanism is not applicable. So the particles can actually not get into motion. Then the third one is excess water that's reporting to the spigot. You cannot have a dry discharge. The water serves as lubricant. The mechanism of the cyclone is of such nature there will always be water present in the underflow. And as long as there's water present in the underflow, there's going to be fines. Ultrafine material, very fine material follows the path of the water, in some portion follows the path of the water. And the more water you have in the underflow, the more fines is getting misplaced. So the objective is always to minimize the amount of water that is reporting to the underflow of a cyclone. When you look at the efficiency of a hydrocyclone, ideal separation is where you've got, and on the x-axis, you've got particle size. On the left hand, recovery to underflow. And ideal separation is when at a specific particle size, you have perfect separation. All the fine particles go in one direction, all the coarse particles go in a different direction. Unfortunately, actual separation inside a hydrocyclone do not really follow that type of shape. So all the material in the shaded areas is material that's getting misplaced. We're getting coarse material to the overflow, fine material to the underflow, and the objective obviously is to try and minimize it. The bypass water contributes to the amount of fines that is then misplaced to the underflow. When we look at the efficiency of separation of a hydrocyclone, we as suppliers, we are looking at the corrected curve, the yellow curve that you see there, the corrected separation. The reason for doing that is because when you evaluate the efficiency of a cyclone, you can only look at the particles that did participate in the classification process. And the portion of material that got misplaced due to the bypass water did not participate. It just got basically hijacked into a different direction. So we have to exclude them, and then we can evaluate the efficiency of the cyclone. And the steeper this curve, the better the separation. So you will then have a different cut point. So we've got a D50 actual cut point and a D50 corrected cut point. D50 is the particle size where you've got a 50-50% probability of reporting either to overflow or to underflow. So three parameters define the strong curve. It's the cut point, the bypass water, and the bypass water or the alpha water is defined as water in the underflow divided by water in the feed. So effectively what we're saying is your water in the underflow needs to be as small as possible and the water in the feed needs to be as much as possible. Then you've got the minimum bypass effect. And then also the imperfection, which is then looking at the D75 and D25 size fractions as well. So in the corrected curve, you've got your D25, your 25% probability reporting to underflow, your 50% and your 75%, and the imperfection is then the slope that you see on that curve. And the steeper the slope, the lower the imperfection, the better the efficiency of separation. On the alpha water, on the actual curves, as we start to decrease the amount of water in the underflow and increase the amount of water in the feed, the curves starts to become sharper, and that's what we're looking for. We want to give the cyclone the best opportunity possible to classify as efficiently as possible. This actual curve is what the cyclone generates inside a milling circuit. So we do have our misplaced material to the overflow. We need to try and minimize as far as possible. And then we've got the misplaced amount of fines in the underflow, where the alpha water is now obviously contributing to a portion of that misplaced fines. So some of the factors that will change the cut point, that will move this curve to the left or to the right, meaning cutting finer or coarser. You change the vortex finder, you can change the cyclone diameter, you change the cyclone length or the cone angle. And when you start looking at the steepness of this curve, then it's the feed density, the solid type of solid density that you are processing. Operating pressure can be applicable to both the efficiency as well as the cut point. And then the slurry split, the volumetric split to underflow, also impacts on the efficiency of the of separation. If you have high volumetric splits to the underflow, this efficiency is not that good. And then you also need just to have a look at just making sure that you've got the optimum operating pressure, optimum spigot settings, those type of factors that is playing a role in terms of the efficiency of separation. Open circuit milling. Open circuit milling is cyclones in open circuit milling is treated as a normal conventional cyclone. So you will make changes around the cyclone, and those changes will reflect then in terms of the mass split to underflow and mass split to overflow. If you make changes within the cyclone, your overflow size distribution do change. We tend to, when we select cyclones for these applications, we tend to keep the overflow size distribution finer than the P80 that is being produced by the milling circuit. That is to ensure that we do not bypass any material that should have gone to a milling application or to the milling circuit in order to get liberated a bit more. Water is sometimes added in the mill discharge sump before moving on to the next process. If those type of installations do exist in your process, the recommendation is to consider moving the water to the feed of the cyclone, because you do not disturb the water balance, but you help to reduce the feed density to the cyclone and thereby optimize the classification efficiency of the cyclone in an open circuit milling application. That's all on open circuit. Moving then on to the closed circuit milling. So closed circuit milling is where material enters into the mill. Mill discharge returns then to the feed to the cyclone. Cyclone underflow back to the mill, and then the overflow leaves the circuit. So I'll come back to this. You will see this flow diagram a couple of times in this presentation, so I'm not going to go in too much detail explaining it right now. But at this stage, the cyclone overflow is the stream that's leaving the process, and that's where the P80 or the grind of the circuit is measured. So one of the questions that we sometimes get is that the client feels that, or is observed that the overflow size distribution of the cyclone, which depicts now the final grind, is either out of spec to coarse, or there's a lot of coarse material or misplaced material. And then the question is, what cyclone diameter will you recommend in order to have a finer overflow? Now, the logic makes sense if you think only of the cyclone in isolation. If you make changes around the cyclone, obviously your overflow size distribution can be affected. But in the closed circuit milling application, it's not that simple. So looking at this example, where you've got two identical milling circuits, fixed speed pump, water addition, everything is the same. And it's a hypothetical case to illustrate a point. The only thing that's different is then obviously that the cyclone diameters are different. One is contain a large cyclone, and the other circuit a smaller diameter cyclone. So the question is then, how would the cyclone cut point be different between these two circuits? And the answer is actually quite simple. Larger cyclones cut coarser, smaller cyclones cut finer. So of course, this large cyclone will have a coarser cut point, smaller cyclone a finer cut point. In terms of the circulating load, which one of these two circuits will have the highest circulating load? And sometimes, when you ask this question to people, the answer is the larger cyclone. And you have to think I think the logic there is because it should be larger volumes, it should be a larger cyclone sending more material to the underflow. And that's not the case. Your larger cyclone actually has a smaller circulating load compared to the smaller diameter cyclone. Remember the tonnage, everything is the same in this example. So how come? How is this happening? Well, we've just indicated the cyclone cut point is coarser with a large diameter cyclone. So when the material gets into the mill circuit, the initial stages, the large diameter cyclone sends out more material than what's coming into the mill circuit. And you've got water addition, sump level control, fixed speed pump. As you start to reduce the circulating load, the amount of material that will report back to the mill from this big cyclone, you need to add more water to keep the level. And thereby the feed density reduces and the cut point becomes finer and the circuit will then restabilize. The small cyclone has got a high circulating load because all the material that's initially entering keeps on going back to the mill. And that cannot also be the case. You cannot keep material inside the milling circuit. It needs to reach equilibrium. So eventually the feed density increases to such an extent, because now there's such a high circulating load of solids, you have to cut back on all the water almost, that the feed density then forces this cut point to become coarser, and eventually the circuit will stabilize. So the next question was then, in terms of misplacement to the overflow, which one will have the lowest misplacement? And again, the immediate thinking is large cyclones, but it's not the case. It's the smaller cyclones because of the larger circulating loads. The feed density to the small diameter cyclones is too high. So when you think of a cyclone isolation, a small cyclone should have efficient cut point. But when you start putting it under pressure and the stress with high feed densities, the unit is not going to perform optimally. The grind. And the first question is the first answer is, well, your grind is going to be coarser for the bigger cyclone. And for the finer, smaller cyclone, you should have a different grind, but it's similar. The cyclone grind or the PAT between these two circuits are very similar because the cyclone cannot change that, change the grind. I'll just show you just now. Just to illustrate how the circuit do stabilize itself when you change cyclones in your milling circuit. As you change the feed concentration solids, your cyclone cut point changes. There's a correction factor that's incorporated in the design of hydrocyclones, and that is the mechanism that is coming into play when your circulating load starts to change. That will help your circuit, your cyclone and mill to reach equilibrium again. Coming back to the comment about the grind of the circuit. So how is it that the cyclone is not affecting the PAT? Well, if you look at the cyclone and the mill as a black box, what enters into this black box is a certain feed size distribution, certain ore hardness, some efficiency factors that's incorporated with the mill, and a certain tons per hour. And what's leaving the circuit, obviously, a certain grind. The equation on the top is the energy equation, the bond to work index, the bond equation. And in there is the work index, the tons per hour, final grind, feed size distribution, and the correction factors. Nowhere is there any reference made to hydrocyclone. So why should the cyclone then impact on the PAT value or the grind of the circuit? And that is for many people difficult to get a handle on, because it's true, there is no reference made to the hydrocyclone. So where does the hydrocyclone then have an impact? And we'll just discuss it in the upcoming slides. So where does our problem lie in terms of understanding the mill circuit the mill and the cyclone as being unity. Why do we battle with that? And that is because when we start looking at designing a circuit, we look at the overall energy input. We then look at sizing the mill, and that conditions the feed conditions to the cyclones, then giving to a supplier to say, okay, size the cyclone in its separately, which we are going to combine with the mill, and that's going to be the package that we will then install on an operation. So the thinking most of the times is that the cyclone is operating, whenever you're making changes around the cyclone, that changes will reflect in the final stream leaving the circuit. But when you do those changes in a real life application, people realize that's not the case. And it's because we tend to have this mindset that the cyclone and the mill is sometimes disjointed from each other while it's not. And that is why it's so important to understand how the cyclone operates, but also how it operates in conjunction with the mill itself. So where does the cyclone, or how can the cyclone have an impact on the mill circuit? Now here's an alternative view or alternative way of describing the interaction between the mill and the cyclone. This is from a company called Metcom in Canada. They present milling courses, and this is information from their training material. So how they describe this circuit is that you've got two inputs, ore and energy. It makes sense. You have an output of that milling circuit, and that's now obviously the production rate of the fines. And then the actions inside this black box are twofold. Grinding of coarse particles, which makes sense, from the mill, and then the removal of the fine particles, and that's where the cyclone comes into play. So there's two efficiencies: grinding environment and a classification efficiency system. So the output from this circuit is the input times or multiplied by the efficiencies that is being determined inside the circuit. Now, I'm not going to belabor too much, not spend too much time on this, but just to illustrate, there's your circuit output, there's the input and efficiencies. That input they break down then into mill power and ore grindability, and the efficiencies, classification system efficiency, and ball grinding efficiency. By rearranging this, you can then get back to a final circuit output. What is interesting from this equation is that now there is a reference made to the classification aspect. This classification, however, is referenced to the amount of fines that's in the underflow of a hydrocyclone going back into a mill system. The more fines that's present, the lower the classification efficiency. And the less fines, the better the classification efficiency. Because the logic is that the energy that's present in the mill circuit should be spent only on the coarser material. So if there's more fines, then the overall efficiency of your mill circuit deteriorates because you're wasting energy. I'll go back at the end just to talk a bit more about what we've just discussed. Something else in terms of the relationship between the classifier and the circulating load. Hoekey, many years ago, 1979, did some test work, and they found that as you change the efficiency of your classification unit, you could actually increase the throughput in a milling circuit. And it makes sense. We just discussed it. If we can have a better classification efficiency, then obviously we don't overgrind on the material. We can allow to accommodate more material into the circuit. So if we now, just for the sake of this example, look at if you had a perfect classifier. As the circulating load increases, your mill efficiency increases. And the reason for that, you have perfect classification. Higher circulating loads decrease the retention time inside the mill. So you are reducing overgrinding, and therefore your mill is operating more efficiently. So a mill in itself actually wants very high circulating loads. However, when we start looking at the cyclone as a classification unit in a mill circuit, we see that the efficiency deteriorates. Classification efficiency deteriorates as the circulating load increases. And the reason is that if we want a steep efficiency curve, we need low solids concentrations and low volumetric split to the underflow. Now, as your circulating load increases, the volumetric split to the underflow increase as well. So that's working against the efficiency of the cyclone. So high solids concentrations, high volumetric splits, that reduces the efficiency of separation. We have more misplaced material in either the overflow or underflow, or in both. If we then look at it more simplistically, as the circulating load increases, the cyclone or classifier efficiency decreases. When we look at classification efficiency, our reference is between the overflow and the feed. You look at the 95% passing size, or let me just explain what we're looking at here. You've got the overflow size distribution, the feed size distribution of the cyclone, and the underflow size distribution of the cyclone. The picture here at the bottom indicates the mass split across that cyclone. So you look at the 95% passing size in the overflow. You know what tons is leaving the overflow. So we know 95% of the tons in the overflow can be calculated. That same size fraction, extrapolate it to the feed section. Look at the percent passing in the feed, and you know what tons is going into the feed. And by doing then a mass calculation, we can then get to the classification efficiency. So for the sake of this discussion, in terms of classification efficiency, that is the formula that has been used, and that is a general formula used in the industry. Again, do not confuse it with the separation or the Tronc curve. That's just another mechanism how we as suppliers evaluate then the efficiency of a hydrocyclone. Coming back then, we sit with the mill efficiency and circulating load, classifier efficiency and circulating load. And when you bring them on top of each other, there's an optimum. And that is what we with hydrocyclones are trying to achieve. We want to maintain the circulating load in an optimum region. We don't want to operate at a too low circulating load because the classifier likes that, but the mill doesn't like that. But we can't go to the other side as well, because although the mill likes it, the classifier is not operating efficiently. So the whole objective in getting a balance or optimum mill cyclone combination is to operate at the optimum circulating load range. Now, in this example, there is the P80 that's leaving through the overflow. And we need, as suppliers, we need that piece of information in order to start our selection with a mill cyclone. The P80, and on this curve, we've got the purple line, which is the overflow of the cyclone. The light blue line, that is the feed, and the green line, which is the underflow size distribution. The red line is the partition curve that was used to generate the overflow and underflow. So in a mill circuit, we've got that P80 value leaving the circuit, the grind of the circuit. That is the overflow size distribution P80 reference point. But we as suppliers need to get onto the red curve, because we're looking at the D50 corrected cut point, as well as then the formula used and generating this curve in order to determine what cyclone is going to be optimal. By going from one curve to another one, there is a correction factor. And all suppliers incorporate a correction factor to go from a P80 value to a D50 corrected cut point. The reason for showing you this curve is there's two reasons. One is often we get the question, why is the cyclone cut point coarser than the grind of the circuit? And unless you are looking at the total picture, it's very difficult to visualize that. There's the grind and there's the D50. When you go to P90s and P95 values on a grind circuit, you will find that your cut point will be finer or a lower value than your P95 value. But if you go coarser, your cut point will always be coarser than the values lower than P80, going to P70 and P60. The second reason for showing you this is that there is a relationship between the overflow and the cut point, this correction factor. And if you are looking at a cyclone to produce a different overflow size distribution, so you want a cyclone to have a finer cut point. As soon as you move this cut point, this overflow size distribution needs to move as well. But the overflow is a function of the grind. And the grind is a function of the amount of energy that you introduce. So you cannot really move this overflow point. And that's where the difficulty comes in and where problems start, where people tend to have an idea, change the cyclone dimensions, and then they see nothing happens, and sometimes it even becomes worse. In a general or the typical closed circuit milling unit is where the feed enters either in the mill back end, but you can also have material entering the mill discharge, feeding to the cyclone, and you then have the underflow returning to the mill and the overflow leaving for the next circuit. The amount of water that you can add into this circuit is dictated by whatever overflow density is required for the next process downstream. So although sometimes we say add water to help the cyclone with its feed density, to make the feed density lower, in a closed circuit mill, it's not that simple. Whatever water you add reflects in the overflow, and there's one of the problems where if you've got very high overflow densities, it means by default your cyclone is already having a difficult separation because you cannot add a lot of water. The cyclone cut point influences circulating load and not the overflow size distribution. We've talked about it now. I believe that we understand that concept. And then the feed solids concentration to the cyclone is influenced by the circulating load and the amount of water that you can add. So if you've got high density, or let me say, sometimes you have applications where you've got a high feed overflow density going to a leach circuit or flotation circuit, and in addition, you've got very high circulating loads, 400, 500, sometimes 600%. And then the client says, my cyclones is not operating efficiently. But Mr. Client, there's too little water. There's so much solids going around. And then the question comes in, but why is those circulating loads so high? Something else has changed in the circuit. If we have high density circuits, one of the options is to look at incorporating dewatering cyclones on the overflow of the mill cyclone. Now that allows us to add a lot of water. So, or either you add a lot of water, maybe I just get the sequence right. You add a lot of water and then you put your watering cyclones on the overflow of the mill cyclone to remove the water again. That is one possibility. When you've got very fine grinds or a lot of clay in your circuit, unfortunately, this option may not be optimal because you return the overflow of the dewatering cyclones back into the process. It serves also as makeup water. And then the underflow of this dewatering cyclones will go then at the correct density to the next process. But in this type of application, the bypass water or the alpha water that we talked about earlier, that's now a problem with short-circuiting fines. Actually, here we need that mechanism. So that's how the circuit can stabilize itself. So it's possible, we just need to treat it with care. But that's one option of reducing the feed density to a primary cyclone, thereby reducing the amount of misplaced fines to the underflow. Because the bypass water, that formula was the water in the underflow divided by the water in the feed. We can make the spigot as small as possible before it goes into roping, but then we need to add water in the feed. And if there's not a lot of water in the feed to the cyclone, your cyclone is still not operating efficiently. There is another circuit. It's not that common these days anymore, but you can include a secondary mill cyclone on this overflow. That will be a scalping cyclone. That will then take care of any misplaced coarse material in the overflow of this primary cyclone. If you've got a lot of water in the feed to the primary at this point, we help with the separation efficiency, but we're more focused now on the fines. But if there's still some misplaced coarse material, you can incorporate a second cyclone. But those circuits are they're becoming expensive, and people tend to move away from them. They try to move to simplicity, and that's where the single mill cyclones is then coming into the equation. The short cyclones do have their shortcomings. At very coarse grinds, screens are the better option. Normally, if we go to grinds about P80 of 180 microns and larger, then we would recommend screens. Unfortunately, sometimes clients do not want screens. They want to stay with the cyclones, and then we need to make the client aware that the cyclone is now operating outside its optimum realm. And then the other area where screens are a better option is with multi-density material. When you've got multi-density or heterogeneous material going into a cyclone, then the cyclone actually separates on mass, not on size. We talk about size when we're talking homogeneous material because it's only one density relevant. But multi-density material, we need to go a bit further and refer to the mass aspect. And that's where the cyclone then falls short, is that the high-density material is getting classified finer, and in other words, there would be a higher circulating load of that high-density material. And sometimes in a mill circuit, that is not wanted. So those are two of the primary areas where cyclones are not at its best. If we start looking at some installations of mill cyclones, you have a vertical orientation in the picture here. That's where the cyclone is positioned. So that's the feed line into the cyclone, overflow and underflow. With a vertical installation, you've got a hydrostatic head because the cyclone is full of slurry. So you need to make your spigot as small as possible. Otherwise, it just want to push down the slurry back into the underflow into the mill. So the spigot diameter needs to be selected as closely as possible to the optimum diameter to provide optimum densities. But when you've got fluctuating circulating loads, then you can easily go into a roping condition because you are operating on the verge of your spigot design, and any additional tons via the circulating load ropes then the cyclone. And that's not the situation that you want, because during roping, when you overload your spigot, the coarse material is then reporting to the overflow and obviously defeating the objective of classification. Also, high wear on the spigot. The other option, inclined cyclones. So that is cyclones that's lying on its side, 15 or 20 degrees to the horizontal. Because the cyclone is lying on its side, the hydrostatic head is much lower and you can afford to open up the spigot diameter. That assists with handling fluctuating circulating loads. So it's advantageous in certain applications. However, we can, in my opinion, maximum of about 4 cyclones that can be installed next to each other from having a common feed distribution point. More than that, the distribution areas can start to occur. So for very high capacity circuits, maybe that having inclined cyclones is not the optimum solution. But where possible, we can afford to have 1 to 4 inclined cyclones. That is a possibility to look at. With inclined cyclones, if you've got high density circuits, in other words, the overflow density goes to flotation and leaching, which is high densities, and not to a thickener, which we see as a low density application, then vertical cyclones tend to have a slightly better efficiency in terms of misplacement of coarse material to the overflow. If you have low density circuits, vertical or inclined will perform very similar. So inclined cyclones, also a viable option to consider. Just to remind you again, that will be a fluctuating circulating loads. If you've got a stable circuit, vertical cyclones is possibly the best option. Then flat bottom cyclones. Not common in milling circuits, but there are indeed applications where people want to use them. A flat bottom cyclone, it's a normal cyclone with some barrels, standard barrel sections, but the bottom end cone section is not. It's got a cone angle of about 150 degrees. These units are normally used when you've got coarse grinds or you require a coarse cut point, but the volumetric flow rates is not high enough to allow you to use large diameter cyclones. So that is the most common area where we would be looking at using flat bottom cyclones. There is, however, when you are looking at coarse grinds, very coarse grinds, this P80 of 180 and coarser, that is also the cyclones that we start to consider to help maintain the circulating load at those high or coarse grinds. When you are trying to use a conventional cyclone at these very coarse grinds, you are going to generate very high circulating loads. And high circulating loads translates then to inefficient cyclone feed conditions, and that translates then to misplaced material. So the objective is, again, keep the circulating load around the optimum as far as possible, and then play around with the cyclone configuration so that you can get a cut point that would be suitable for those conditions. The two-stage cyclones that I briefly mentioned earlier, you've got in this picture here, a primary cyclone. Overflow then gravitates to a secondary cyclone, and then the underflow of the secondary cyclone, discharge to the mill discharge, not to the mill feed. And the primary cyclone underflow obviously to the mill feed. So this is to help to reduce misplaced coarse material that is getting misplaced by the primary cyclone. It works well in low density circuits. If you've got a high density circuit, a two-stage unit is not going to work. The reason for that is that your secondary cyclone will still have acceptable feed conditions, but your primary cyclone is going to operate at much higher feed densities, and that will render that cyclone inefficient. Dewatering cyclones, in some applications, it's possible to, we've mentioned about incorporating dewatering cyclones when you have a lot of water in your circuit. And these are the type of units that we are looking at. We say here that equivalent to thickness, we need to just see that in context. That's when you've got not a lot of fine material. Thickness is still the best unit to produce clarified water or clear water. But there are cases where cyclones can be considered or evaluated and see if there is merit in looking at those units. So we say here that it is possible to replace the thickness, but we need to be careful. I need to put it just clear or explain it better. It's when the material that is going to, that the amount of fines that's present, that the amount of fines is not so high. So your relative coarse material, that will do the job. Otherwise, thickness is still the option to look at. But dewatering cyclones in milling circuits, again, option to look at unless you've got very high amount of fines or clay material. Moving then to circuit optimization, closed circuit optimization. We know now that there's in the mill circuit, there are some factors that's incorporated to select the mill, and the cyclone and mill should be seen preferentially as a black box We know that the circulating load needs to be a optimum. There's an optimum value for circulating load. You know that there's a relationship between the cyclone overflow and the cyclone cut point. And what the objective is that we want the overflow to be as steep as possible, the overflow size distribution to be as steep as possible. But again, the PAT value will remain unchanged unless you make changes to the mole circuit itself. We have discussed now the effect of changing or trying to change the cut point of a hydrocyclone in a mole circuit in trying to influence then the grind. That is not going to work. If the circulating load is much lower, then it's a different story, because then you may need to reduce the cut point in order to generate higher circulating loads, and the mole by itself will then possibly produce a better grind, not the cyclone, the mole. The effect of circulating load, we've talked about that. Just to keep that in mind, our reference is circulating load. If the circulating load is too high, we know there's a problem. The question is then, why is there a problem? You cannot change the cyclone before we find out what's going on in the circuit. And obviously if the circulating load is so low, why the low circulating loads? And then what can we do with hydrocyclones to assist the mole circuit itself? Then the control philosophy. In this example, the plant was controlling on slurry density, and there was incoming volumetric flow rate from a different circuit, and that resulted then in spikes in the flow control to the cyclone and operating pressure. The result was that sometimes the cyclones will experience maximum flow. The cyclones will go into a roping condition. It will then misplace coarse material to the overflow, and they started to get beaching, sanding up of the leach tanks. The suggestion was then to go to level control the volume, fixed volume to the cyclones, and let the feed density fluctuate. So that's maybe I haven't included a slide on that topic, but just in terms of the control philosophies on a milling circuit, if you have constant volume flow, then by allowing the density to drift, you can maintain the circulating load more adequately. If you try to maintain a constant feed density to the mole cyclone, the only time where that really works is when you have very stable conditions going into your circuit. Otherwise, the circuit can become a bit of a problem. The best control philosophy on a mole circuit, however, is if you measure the overflow PAT value, the grind, and you link that control mechanism to the feed to the plant, because that is where you then really maximize your mole performance. You match your energy to your PAT, but those type of installations are not very common. But that is the right way of maximizing your mole circuit. Measure the end result, control the input values. In terms of the effect of change of grind, a client contacted me and asked what must he do around his cyclone, because his overflow, and this is the blue line that is running here, starts to produce much more coarse material that's going on to the next process, which is leach. So then there was too little amount of information, so the other information was to ask what is the circulating load looking at, and that information was produced. And one can see the correlation between higher circulating loads and the amount of misplaced material in the overflow of the cyclone. So the question again, what has changed in that circuit? What has caused this circuit to increase in circulating load? And they admitted they're trying to push tons. That made the grind coarser, and the cyclone was just generating higher and higher circulating loads. You have situations where the overflow size distribution in general is quite good. Over time, the cyclone is either neglected or something changed inside the cyclone. The PAT remains the same, but there is more misplaced material, and that's depicted by this yellow line. And then the request is, but we're looking for smaller diameter cyclones because we have too much misplaced material in the overflow. Now, if you look at the smaller diameter cyclone, where in theory you want a finer overflow, then it means that your PAT is going to be finer in the overflow of the cyclone. But we're in a mill circuit, so we cannot make that change. And the more you think about the question, it's maybe not that they want to change the grind. They just want to minimize the amount of coarse misplaced material that is present. That comes back to looking at the feed conditions to a mill cyclone, so that we can see how far can we improve the amount of misplaced coarse material. Because, to reiterate, the cyclone does not control that PAT value. It's an energy-related mechanism. So I mentioned this earlier to you. We've looked at this the second description of how the cyclone and the mill interact, and we said that there is this equation, and there is a Ball-mill power factor. There is a classification system efficiency factor, all grindability, that's all related. So that you cannot change, but then there's all ball-mill grinding efficiency. So there are 3 or 4 factors that influence your circuit output, and it's not only the cyclone. So if we start looking at just in summary, Waldo has already talked about that to a certain extent. Ball-mill power, you got volumetric ball loading, mill speed, media selection, internal profiles of the liners, discharge design, water usage. Those are factors to look at the ball-mill power. Then on the classification system efficiency, the cyclone, hydrocyclone for water usage. Add water if possible, because we want the feed density of the cyclone to be as low as possible. But the reason for that is we reduce misplacement to the overflow and fines to the underflow. We don't want to send unnecessary fines to back into the mill. The circulating load, running at the optimum circulating load. Multi-stage hydrocycloning, something that we've discussed in this presentation. Use of high efficiency classifiers. These days, most of the suppliers across the world, the equipment is quite similar. That's good quality. The efficiencies, one cannot find any fault with the efficiencies, but there are some older designs or in areas where people are making their own cyclones to save cost, where there could be a benefit of looking at a new modern design. Ball-mill discharge design, water usage, also factors to keep in mind or to look at for the classification system efficiency, and then ball-mill grinding efficiency. Water usage, grinding media, material, shape, motion, as well then as the last factor. Point on this slide is that if you want to optimize your mill circuit, the cyclone is only but a small area to focus on. Most of the work and most of the factors that will have impact relates to the mill itself. However, sometimes people think we will make a quick change around the cyclone and it's going to solve our problem. Some circuit checks. We sample normally with a Marcy scale and a beaker. Make sure that the Marcy scale is calibrated because we need accurate information. The Marcy scale beaker has got 2 holes. Make sure that we take the sample. When you take the sample, you close the holes, remove the bucket after you've taken the sample, remove your fingers at the beaker drain, put your fingers back or walk to the scale. Otherwise, you get settlement of solids, and then when you drain the excess volume, you're only draining water, wrong information. Sampling around the circuit, cyclone overflow, underflow, and feed is what we require. Sometimes it's difficult to sample the feed to the cyclone. The pressure gauge port can be used as a sampling mechanism by making up a TPs. The results in terms of sampling needs to be accurate as possible. Poor data leads to information that we cannot really use. So make sure that you sample correctly, because you use this information to generate a mass balance around the cyclone. From the mass balance, you can generate idea of what's you can calculate the circulating load. And if you know what's the operating pressure to the unit, we can then look at what the volumetric flow rate of the cyclone is. Back calculate, get the tons to the cyclone, you know the circulating load, and you can complete the overall mass balance between the cyclone and the mill itself. But it needs to be based on accurate data. Visual inspections of this of the underflow of the cyclone, quite useful. When the discharge is too dilute, no good. Roping also means course misplacement. Optimum discharge, that's what we are looking for. Also, we can evaluate do a mass balance around the overall mill circuit, but we need the feed tons, product density, cyclone overflow density, circulating load, cyclone feed density or percent solids to the cyclone feed, and the underflow, and we can complete the overall mass balance. Looking at the cyclone, get an idea of where the cut point is to check, is this a relationship? Is there a problem between this relationship between the overflow and the underflow? Is your cyclone still the correct piece of kit? Looking at trends, very useful. That gives an indication if there's any instability. It can help you as well. Then some general guidelines. Pressure gauge, that will help us to indicate, to get the indication, will help you to get indication if the cyclone is operating correctly or not. The picture on the right hand side, cyclone distributor, there's no pressure gauges because there's a common pressure gauge on the feed distributor. But pressure gauge, very important piece of kit to have, a working pressure gauge. Check the speaker diameter, make sure that the densities, to make sure that you have adequate underflow densities. Speaker discharge, sometimes you get blockages. Checking the cyclone internally during maintenance, if that is possible, because we don't know, you cannot assume if something comes out of the overflow and underflow that cyclone is operating correctly all the time. Over time it wears. The feed conditions to the plant as far as possible constant, and determine where's your losses. So if there's a grind, there's a problem in your plant, and I think most people know that, look at your tails, do a mineral deportment, see what size fraction is the one that's problematic. Is the coarse material, or is the coarse fraction, or is the fine fraction? And then alternative wear materials on your cyclone. That can help to extend the life and giving you more consistent dimensions. On the Multotec cyclone, there is weepoles that you can use, and let's go back here. They're situated on the sides of the cyclone, and those weepoles gives you indication if the liner is torn. This is something that can be of use for people that uses this option or these cyclones. And then lastly, we've talked about the trommel screen and the importance of having a trommel screen. The photo that I'm showing you now on the screen, gentlemen, I kid you not, it has been coming from the cyclone overflow. That is material that has got discharged through the cyclone overflow. Now, before you think that maybe I'm losing it, the cyclone got blocked because I removed trommel screens and that material started to discharge through the overflow. So if ever you think the cyclone cannot discharge coarse material in the overflow, this is the first time I've seen that. I just put it up for interesting purposes. So in conclusion, the hydrocyclone cannot change the grind. I trust we will now understand that concept. But the cyclone and the mill forms an integral relationship, and that we need to understand. But don't forget about the pump, the sump, and the instruments. Constant level control, constant operation, all impact on how the cyclone operates, and then the impact it can have on the mill itself. Getting proper and correct information is sometimes the biggest challenge, because you cannot work with information that is sampled today and the other half of the sample was sampled 2 months ago. That does not work. We need accurate information to give you accurate answers. And then lastly, we can assist. If there's any questions, it's not only about sales, it's to support the clients, to assist, giving you some ideas. You're more than welcome to give us a call. So in that, thank you very much, and thank you for the opportunity to present.